All right, chapter 8 here. All right, so week 8 here has us starting with springs. So springs are really important physical systems, and so it's really important that we spend a bit of time trying to understand their character, maybe before you start the reading. So when you think about a spring, I want you to think about something that wants to exist at a certain length, okay? So if that spring is connected to an object, it might exert a force on that object in order to get back to that length. Now that tendency to return to that length actually can produce some interesting motion. So when I think about springs, the first thing that I think about is a couple of different positions, in fact 3 positions. So let's put a mass on a frictionless surface. And then let's put a wall here. And what we're going to do is we're going to attach a spring of spring constant K to that mass. We'll call this the positive x direction. Now, the spring wants to exist at a certain length. We're going to call that the equilibrium position. That position of the mass, we're going to call it x equilibrium, EQ. So if the spring is at that length, and the mass is then at that position, then the force exerted by the spring on the mass is 0. Now it doesn't matter if the mass is moving or not, or if it's stationary. At that position, when the mass returns to that position, the force on the mass will be 0. The spring's at the position that it wants to be. If we draw the same mass, though, and we have the same x equilibrium position, if the mass is over here and the spring is compressed, well, it's too short. So the force that the spring exerts is going to be in that direction. It's going to want to push it back to its equilibrium, to its natural length. And finally, the third case is that now, relative to the same equilibrium position, if the mass is over here and the spring is stretched, well, it's too long. And so the spring wants to return to its length, and so the force by the spring on the mass is in that direction. Okay? So, as you're thinking about this physical picture corresponds to what we call a restoring force, or Hooke's law. That is, the force that the spring exerts is going to be minus k, x minus x equilibrium. So spend a little time with this expression to make sure it comports with sort of this conceptual understanding, because we're going to use this quite a bit. Now the next topic here, which is really kind of an application of springs, is Young's modulus. Now this is really interesting because we have an opportunity to look at real materials. So when you think about springiness of materials, I want you to think about, this sort of example. We have a rod here. We have some kind of a restoring force. The material wants to return to its equilibrium length. And so this restoring force is related to a fundamental property of the material called the Young's modulus. So this expression here looks a lot like this Hooke's law force. We'll assume that this delta L is our delta X, okay? And so this constant in parentheses here, that's our effective spring constant. I encourage you to do example 8.11. It's pretty great, but this is a nice connection between what we're doing, what we're modeling, and some important applications. Take a look at figure 8.23. Okay, so there are a couple of concepts here. There's this tensile strength. Okay, when we look at a stress versus strain curve, okay, the tensile stress or the tensile strength is the point at which the material fails, essentially. Okay, so in figure 8.23, you've got spider silk versus steel, and the interesting thing about these two materials is they have the same tensile strength. However, there's a really important difference here. When we look at stress versus strain, you're going to see that the spider silk has a much smaller Young's modulus. Therefore, it can stretch much more in a physical sense than steel does. So steel's Young modulus is about 200 times what spider silk is. So it resists this tendency to compress or stretch a lot more than the spider silk, although they both break under the same tensile stress. So spend some time, get comfortable with these concepts. Springs first, then the application using Young's modulus. The Young's modulus actually controls a lot of different properties of the material. So just know that we're playing around with its reaction to being stretched or compressed, but it also influences things like the speed of sound through a material, okay, or how vibrations propagate through. So have a little fun, and make sure, as always, to come and chat about any questions that you have.